Philosophy of modern physics. Newton used geometry to derive and construct the law of gravity from the moon orbit. Gauss and Faraday create an empirical law from an experiment, later become Maxwell equations for electromagnetic. It seems like all the fundamental law of nature derives from observations. Suddenly, the 20th century comes with the change. Underlying law was derived from the powerful novel method. It's all started with Einstein. In 1900, Albert Einstein began his life with graduations and job hunting. It's been 2 years of seeking a solid job. Then he got a job at the Swiss Federal Institute of Intellectual Property. He worked there as a patent examiner. Regardless of his full-time job, Einstein continued working on his research idea with his friends and his wife's help. In 1905, Einstein published 4 groundbreaking works: special relativity, Brownian motion and atoms, mass-energy equivalence, and photoelectric. All of these works could be called paradigm shift. Here's where Einstein graduated from: ETH Zurich. Einstein studied his bachelor's degree here. He's naturalized his German citizenship and became Swiss citizen in 1901. From the Maxwell equations for electromagnetic to spacetime that bend. At that time, it had been more than 30 years since Maxwell showed that the empirical laws governing electric field and magnetic field predict the existence of so-called electromagnetic wave. The wave equation shows that such a wave's speed depends on 2 physical constants, permittivity and permeability. The dependence on physical properties implies that the speed of light, which is a kind of electromagnetic wave, should also be a constant. But, as we all know, speed is relative to the observer. Physicists at that time wonder which frame the speed of light is as the equation predicted. It must be a constant in the frame of its medium, and let's call the medium which light travels as ether, they guessed. Albert Michelson and Edward Morley then tried to measure the relative speed of the Earth moving through the ether. The result is frankly strange. It shows that if ether existed, we must be moving at the same speed as the ether. This made scientists question the existence of ether. Giff illustrated the experiment of Michelson and Morley. The right one is the case which Earth moving relative to the ether. In 1905, the question was answered by the patent office worker named Einstein. In his work, On the Electrodynamics of Moving Body, he proposed that instead of moving in the medium, the wave needs no medium. The wave instead moves in free space and can be perceived at the same speed from every people's point of view, as long as the frame is inertial. This shockingly proposed don't come alone. It also brought some elegant and weird results. Firstly, it makes every inertial frame equally the same. There's no frame more equal or special than the other. The second and strange one, to get a constant speed of light in every frame of reference, the distance and time measured in each frame need not to be the same. From the hypothesis to the state-of-the-art understanding, Einstein's special relativity predicts the existence of the phenomenon no one had ever experienced before, the time dilation and length contraction. Absolutely no one had ever measured the inequality of time duration, nor the shortening of length. Einstein's prediction indicates that to see the result, one has to move so fast, faster than any locomotive at that time, to see a time dilation of a second. Later, the theory was developed to use within a frame of reference that is not inert, i.e., allowing him and other physicists to predict the behavior of celestial objects like Mercury's orbit. The theory was called the general theory of relativity. Einstein proposed that there's the equivalence of gravity and accelerating frame of reference. Then, the weird things were predicted from the theory. Light can be bent by gravity. The collapsed star can become the source of intensive gravity that breaks the equation, aka black holes. The massive star collapses and produces a gravitational wave. It was tested from time to time, but the theory still holds it together. If it weren't for the theory, no one would have imagined bizarre events like these. Quantum. The discrete and unpredictable universe. It starts with a discretization of emitted energies. Max Planck failed to use the classical idea to describe the radiation of black bodies. Strangely, when he uses the idea of discrete energy level, it worked. Sadly, he didn't know why and was not happy about it. The black body radiation is the radiation of any object with the temperature. The reason people called it black is simply to ignore the reflected part of radiation. However much you shine the light to the black body, it is all absorbed and later radiate back due to the thermal energy. Planck was trying to build the underlying principle to describe how much radiation is in each wavelength. The classical assumption gave him a strange result: the shorter the wavelength, the higher the intensity would be, which is simply wrong. He decided to let the energy of emitted light be multiples of some particular value, then the prediction fits nicely with his result. He called that particular value to be quanta. Discretization of energy and the photons. Later, in 1905, Einstein published the work, namely, on a heuristic point of view about the creation and conversion of light. The work proposed that light, like energies, is discrete, and its quanta are called photons. The problem that led Einstein to the proposal is called the apparent paradox. The paradox concerns about why electrons don't get energized and emit from the conductor when the high intensity of light shines to its surface, but simply increase the frequency does energize the electrons no matter how dim the light is. To explain this, Einstein proposed that electrons receive energy in a quanta manner, like when a black body radiates. That means the light is also quanta. And when the intense light hits the surface of a conductor, a factor that determines if electrons will emit is not how many photons hit but rather how much their energy is. His work also predicted that an emitted electrons must have a linear relation with the incident light frequency. This was proved experimentally by Robert Milligan on his experiment with the oil drop. From discretization to uncertainty, discretization of energies and photons' existence are the first clues toward the duality property of wave and particle, aka wave-particle duality. Louis de Broglie suggested that the electron's momentum and its wavelength are intercorrelated. Momentum is a property in which any particle has, while wavelength is a property of the wave. De Broglie proposed that every particle can be considered as a wave, and its wavelength is according to his equation. The idea of the coexistence of wave and particle led physicists to develop wave mechanics that describe the time evolution of quantum particle. Later on, Erwin Schrödinger proposes a model of electrons in hydrogen atoms through the wave function. The equation is later known as Schrödinger equation. The prediction of his model fits nicely with the experiment result. However, he's not very successful in explaining the physical meaning of wave function, which is the central mathematical object in his equation. While Schrödinger was trying to figure the meaning out, Heisenberg found the interesting intrinsic property of transforming wave and particle back and forth. The property is uncertainty, which generally means that if you can measure a wavelength of the wave precisely, then you can't measure its position precisely and vice versa. Also, the property can be shown via the non-commutativity cannot commute of operators associated with these two quantities. Then, Max Born interprets the wave function as a representation of its probability. That is, given the wave function is fx, then its probability distribution can be given by p(x) equals fx squared. This leads to superposition property, which quantum particles can exist in many states at the same time. As anyone might expect, physicists at that time didn't like the idea that one thing can't be determined exactly. Einstein is also one of those who don't like probabilistic ideas. Later, he showed that it's not complete by a thought experiment. Spooky action at a distance. Something's that faster than light. Einstein thought that the unpredictability of quantum physics led to a severe problem. For example, if some process gives two electrons with total angular momentum equals 0, by superposition, we don't know each particle's angular momentum unless we measure it. The problem is whenever we measure one particle, then the other's angular momentum will be determined immediately, no matter how far apart they are. This suggests that there must be something that communicates between two particles faster than light does, which violates Einstein's theory of relativity. Einstein and his friends figured this scenario out and wrote an article about this problem. You can read it from Can Quantum Mechanical Description of Physical Reality Be Considered Complete? Here, he said that the theory must be incomplete and can be improved. The development of quantum theory is still going until this day under the storm of critical questions and doubts. The theory becomes more and more solid as more people put thought and their hearts into it. It's one of the candidates to build a complete underlying theory for everything. Conclusion. Philosophy of modern physics. In the age of Newton, Gauss, Galileo, people tested and developed their idea from experimental data. Things had changed in the 20th century. From deriving things from empirical law, physicists push the world forward by setting an underlying principle of things and testing it with the greatest extent: black holes, speed of light, and the large distance. They set bizarre assumptions that give a radical prediction, which seem to be a weak point, but will be strong support of the theory if the prediction becomes true. Karl Popper, an English philosopher, born in 1902, gave a proper-ending remark on this. He said that scientific knowledge's crucial property is falsifiable, which means the ability to be false. The falsifiable is when the scientific theory can give a testable prediction, like when Einstein's theory predicts the existence of gravitational wave or quantum physics predict the spooky action at a distance. However, the fake scientific, in Popper's word, pseudoscience, lack this quality. Pseudoscience can't tell the difference between positive tests of their theory apart from a negative one, or even worse, can't be tested anyway. Sometimes it seems like to have a test, but it always depends on the interpretation, not from the principle within the theory itself. The advantage of testable prediction and falsifiable in general is that we can know what is not valid. The test result can't guarantee that the theory or its underlying principles are correct but can tell when it's not. With a great effort and critical way of theoretical development, humanities acquire new knowledge faster, more wonderful, and more powerful than